Welcome to This Explainer. Today, we're diving into a topic that is honestly a little mind-blowing. We're going to explore how a single, seemingly impossible observation completely broke the established rules of crystallography and redefined our very understanding of solid matter. We are looking at a discovery so profound, it literally forced scientists to rewrite the textbooks. Okay, let's jump right into this central mystery. Imagine discovering a solid material that possesses perfect, long-range order, yet totally lacks the translational repetition that scientists believe defined all crystals. Up until this discovery, the scientific community operated under a very strict, uncompromising dogma about how atoms could arrange themselves. So what do you do when the physical evidence sitting right under your microscope tells you that the impossible is, well, actually real?
To unpack all of this, we're going to quickly walk through 5 key areas. First, the initial shock of that impossible discovery. Second, the abstract mathematics that finally made sense of it. Third, the human drama behind the paradigm shift. Fourth, the deeply weird concept of higher dimensional superspace. And finally, the incredible real-world engineering applications.
All right, let's start with part 1, the impossible crystal discovery. We have to trace our story back to a very specific moment in 1982 when the fundamental rules of chemistry were broken.
Before this discovery, everybody thought all crystals perfectly repeated like a simple, predictable grid. That's what we call translational symmetry. Basically, if you know one little section of the crystal, you know the whole thing. But quasicrystals threw a massive wrench in that. They proved that a structure could be mathematically ordered and rigid without ever actually repeating itself. They introduced completely unexpected local 5- or 10-fold rotational symmetries that just didn't fit into the classical models at all.
And here it is. This captures the exact moment the world changed. Notice the bright dots in this actual X-ray diffraction pattern of a rapidly solidified aluminum-manganese alloy. Materials scientist Dan Shechtman observed this, and those dots form a perfect 10-fold symmetry. At the time, established scientific dogma stated unequivocally that this kind of symmetry in a crystal was absolutely impossible. It was a physical contradiction.
Moving to part 2, Penrose tilings. So how could this physical structure actually exist if the laws of crystallography flat out forbade it? Well, the answer wasn't in a chemistry lab. It was in abstract math developed a whole decade earlier.
You have probably seen patterns like these before. These are mathematician Roger Penrose's famous aperiodic tilings. By using just 2 simple geometric shapes, often described as kites and darts or specific rhombi, you get perfect 5-fold symmetry and self-similarity through processes called inflation and deflation. Basically, you can mathematically scale the patterns up or down infinitely. But the true magic here, they perfectly cover a surface, but they never ever repeat over an arbitrarily large area. This completely abstract geometric concept ended up being the exact blueprint needed to understand Shechtman's physical alloy.
Here's the really wild part, though. This mathematical concept isn't entirely new to human history. Think about medieval Islamic mosaics, like the stunning designs found in the Alhambra Palace in Spain, or the Darby Imam Shrine in Iran. They actually used similar mathematical rules to create aperiodic patterns. It is absolutely mind-blowing to realize that ancient artisans were playing with the exact same geometric principles that would later help modern quantum chemists visualize the atomic layout of quasicrystals. I mean, they were literally hundreds of years ahead of 20th century science.
Which brings us to part 3, the scientific paradigm shift. Even with the math starting to align, Dan Shechtman still faced a massive hurdle. He had to convince a deeply, aggressively skeptical scientific community.
And let me tell you, this was not an overnight success story. After his 1982 discovery, Shechtman faced such intense backlash that his lab director actually handed him a basic crystallography textbook and asked him to leave the research group. He was treated like a scientific embarrassment. Because of this profound skepticism, he waited 2 whole years to publish his findings, rigorously defending his data against people who insisted his samples were just flawed. But his perseverance paid off. By 1992, the evidence was so undeniable that it forced the International Union of Crystallography to literally rewrite the definition of what a crystal is. And this incredible journey ultimately earned Shechtman the 2011 Nobel Prize in Chemistry.
Okay, part 4, higher dimensional superspace structures. Now that the existence of quasicrystals was an accepted scientific fact, crystallographers were faced with a brand new headache. How do you map out the complex atomic structure of something that doesn't repeat in standard 3D space?
Because quasicrystals lack a traditional 3D repeating lattice, scientists had to get a bit creative. They adopted what's called a superspace description. Now, to be clear, we aren't talking about literal sci-fi alternate dimensions here. It's a brilliant mathematical trick. By treating the atoms as multi-dimensional objects arranged in a perfectly periodic 5-dimensional or even 6-dimensional cubic lattice, the math suddenly works perfectly. To find out what the physical structure looks like in our normal 3D world, they just mathematically cut a 3D slice out of that higher dimensional space.
When you visualize this superspace concept, you start to see how the atomic surface generates the local arrangement in our physical world. It also highlights something incredibly unique to quasicrystals called phasons. You can think of phasons as tiny spatial jiggles. It's this dynamic, fluctuating order. Instead of being perfectly rigid, these little atomic shuffles actually help keep the entire overarching structure perfectly stable. It's a flexibility that normal periodic crystals just do not have. To further decode these complex environments, scientists study what are known as approximates. Basically, these are regular, periodic crystal structures that have very similar local atomic arrangements to the quasicrystal itself. By making rational mathematical cuts through that 6-dimensional hyperspace, rather than the irrational cuts that give you true quasicrystals, we get these approximates. They provide vital, solvable clues that help scientists sort of reverse engineer the true aperiodic structure.
And that brings us to part 5, architectural and material applications. This isn't just theoretical math and high-dimensional physics locked away in a university lab, right? This paradigm shift has birthed incredible new materials that you might actually interact with.
So why does this matter to us? What do we actually use quasicrystals for? Well, because of their unique, non-repeating atomic structure, they possess highly unusual properties. They have extremely low friction and amazing corrosion resistance. They interact with light and heat in entirely novel ways. This has led to advanced applications like selective solar absorbers for better power conversion, highly efficient thermal insulating coatings, and even highly durable, biocompatible materials used in bone repair and joint prostheses. It's a real game changer.
And we're scaling this concept way up, moving beyond microscopic materials to macroscopic engineering. These aperiodic tiling structures are actively replacing traditional hexagonal honeycombs in structural design. By using quasicrystal-inspired patterns, engineers are creating composite materials with a rare and highly sought-after property, a zero-Poisson's ratio. Essentially, this means when you compress or stretch the material, it refuses to bulge or deform on its sides. It drastically improves strength and toughness, and it's a structural concept that is already influencing modern architectural marvels, like the facade geometries they considered for the Transbay Transit Center.
As we wrap up this explainer, I want to leave you with this final thought. Dan Shechtman looked through a microscope, saw something impossible, and fundamentally changed the definition of chemistry. Roger Penrose played with geometric tiles and unlocked a 6-dimensional mathematical mystery. If this aperiodic mathematics has already completely rewritten the laws of atomic solids, how will these non-repeating patterns shape the skylines, the bridges, and the structural marvels of our future? The blueprint for the impossible is right in front of us. Thanks for joining me.